Welcome to the Cosmic Pie podcast. So this is episode number 7. I'm your host, Wayne Barkhouse, and with me is...
Robert Moore. Nice to meet everyone.
We're broadcasting live here from the campus of the University of North Dakota in Grand Forks, North Dakota. Robert, do you know what is the sign of a healthy campus?
Sign of a healthy campus. Nobody going to the infirmary?
Keep going.
Oh, okay.
Another answer?
People on campus.
Another answer? That's a good one, yes.
Okay.
Keep going.
Nobody walking around coughing their heads off? I don't know. I'm kind of stabbing in the dark here.
Construction, Robert.
Oh, that is a good one.
Yes, of lots of ongoing activities on campus, as there is today. So if anyone hears some banging or noises in the background, that's what's happening. We're undergoing some renovations here in the building that we're broadcasting live from. So that is a sign of a healthy campus.
Good point. I was dodging all over the place and not coming up with that one.
I was just going to see how long it would take you, but I feel your pain.
Yeah.
I didn't want to...
I was thinking personal health and not campus health.
Exactly.
But yes.
Now, if any of you have any questions you'd like to ask us, we do have a live chat that's running, so please entertain us with your questions, and we'll try to answer the best as possible. If we don't know the answers to them, then we'll just make them up like normal, right, Robert?
Right. No. We'll figure it out, and we'll have it on a full show on it next time, or in the future.
Isn't that what a lot of people do on the internet? You just...
A lot of people like to make things up, yeah.
Okay. Well, we won't go down that route, right?
No, that's a rabbit hole I don't like crawling into.
Well, there you go.
I'd rather admit ignorance. Thank you.
Okay, so some of the interesting things that appeared in the news lately this week. There's been a report that we mentioned a little bit, I think, in the past, but we didn't really dive down into it in any great detail. So this is the issue that astronomers are having with the huge number of satellites that are in orbit around the Earth and the effect that they have on the long exposure images that we take of the night sky.
Yeah.
You know, one of the things in astronomy that we do is that we like to look at things as faint as possible. We don't look at always at faint things, but normally we like to. At least a good part of astronomy and astrophysics is related to that. And to see things as faint as possible, you take a very long exposure with your camera. Now, normally, if you do photography, daytime scenes, you don't have to worry about the exposure time. Person usually has their camera set to auto setting, and it's usually a fraction of a second given the ambient light that's around at whatever object they're looking at. But in astronomy, we want to traditionally look at things that are extremely faint, which means long exposures, some of them, hours in length.
Right. I like pointing out to people that the sun has an intensity at the surface of Earth of approximately now 1,000 watts per square meter. And if you're not familiar with what a watt per square meter means, don't worry about it. I'll fix that. So 1,000 watts per square meter. To put it in relation, that's enough energy to run about 3 dryers. But the brightest star, Sirius, has an output on the surface of the Earth of about 10 to the minus 8 watts per square meter. So we're going from 10 to the third watts per square meter to 10 to the minus 8, a difference of over 1 billion. So this is why we like long exposures with astronomy. We're dealing with things that are 1 billion times dimmer than the daytime sun.
Right, so a hamster running in a cage can generate more energy than what we receive from typical stars in the sky.
Absolutely. Probably a few orders of magnitude.
Exactly. So in astronomy, when we look at things far away and things that are very faint, we need to take long exposures. But if there are satellites in orbit above our telescopes, so you can think of it in terms of ground-based telescopes or even telescopes that happen to be in low Earth orbit, chances are that a satellite will move in front of the field of view or in front of the camera, and you'll get this trail, if you like, this streak across your image.
Yep.
And that's what was in the news today. So, Robert, if you want to show the first slide. So these are images that have been taken over several years from the Hubble Space Telescope, and it was a paper that was just published in Nature Astronomy. And what it deals with is essentially the satellite trails that were observed or that were captured by the Hubble during the normal exposures that it was making of various objects in the sky. And one of the things you have to think about, so the way to look at it, there are different postage stamps here. And the top panel is sort of the raw type of images. In the bottom part in the panel, the lower half, is the attempt of astronomers to use various types of software to try to eliminate those streaks. And you can see in a lot of cases, or at least in some cases, I guess to be fair, you can't remove them.
You can't remove it. You really can't.
So and to get rid of it, you have to take another image. But
Right.
time on the Hubble is precious, so they're not going to necessarily give you time just so you redo your images because there happened to be a satellite pass in front of the camera at the time.
You just have to hope it didn't pass in front of your target.
That's right. And so this is becoming more of an issue lately, and because of all of the satellites that are being put up into space, and we won't mention the various companies, I don't think. We don't
I
need
don't
to do
think
that.
it's needed. You know, I think they'll be aware of who we're talking about, and
Right. And you can Google it, of course, to look up this kind of issue. But it's becoming more of an issue. The larger the number of satellites in terms of sheer volume of the numbers that we put up, it just increases the odds that at a given time you're doing exposure of some object, you're going to have a satellite that encroaches your field of view, right? That passes in front of your camera.
it's a similar issue, honestly, with a ground-based telescope. You have to have satellites, and if you're like I used to be near a major airport like Atlanta, a lot of times I would have airplanes go through my images. And in fact, one of my favorite images is a shot I took of the Horsehead Nebula. And you can see this green streak stop and a red streak pick up. And I know it was an airplane because of that parallel streaks, except for where one started, the other stopped. And so, ground-based and now apparently space-based, you still have the same problem with the satellites.
Right, and there is processing you can do. I mean, I've had situations where I've been in that scenario where I had to remove streaks from images, and the typical way of doing it is you take multiple images of the same pointing in the sky of the same object, and you can combine those images in such a way that you can get rid of those streaks. There's ways to handle that from a software point of view, but that usually requires taking multiple images.
And let's face it, if your target is so dim on Hubble that you need a 10-hour exposure and you have 11 hours, you don't have time to go back and reshoot that.
Well, you are going to have multiple exposure because remember, Hubble's in orbit around the Earth.
True.
Right? So you have at most, almost 45 minutes for a given exposure because the telescope would be on the other side of the Earth.
Right.
Yeah. So you have to break your images. But if, let's say that you were awarded time, I don't know, let's say 20 minutes.
Right.
And you need all 20 minutes to take one image. And that's all you have. You have nothing else. And then when you look at your image, you find there's a bright streak running across the center of it due to a satellite that happened to be passing across the field of view. Then what do you do at that point? Then you're kind of stuck.
Right.
Right? You kind of got to, there's no useful information then that would come from that part of the image in that sense.
And Wondergoon's asked a question. Do either of you think we will ever get to the point of cleaning up the debris in orbit? And the answer to that is, for me, is yes, no. Yes, we will get to where the garbage, the junk, is going to be cleaned up. We'll have to find a way of doing that. The thing is as technology increases and everything, we're going to be putting up more and more, not debris, but satellites, period, to cover all the bandwidth and everything that all these communication companies need. So, while yes, I think we'll clean up the trash, I think the problem is only going to get worse as far as the actual number of satellites that are up there.
Well, here's one way of thinking about it. So anytime you put up a satellite in orbit around the Earth, there's always unintended debris that comes from it, a shedding process. It could be different, particles of things like, a bolt, a washer, these kind of things. And because they're traveling on the order of 5 miles per second on average,
right,
that impacting an oppositely approaching vehicle, let's say a International Space Station that's also traveling at roughly 5 miles per second in the opposite direction, that relative motion is 10 miles per second.
Right.
Right. So that can cause
That's a lot of energy.
That can cause major damage, even if what you're talking about is the size of a washer. In fact, we've known that on several of the missions of the space shuttle, when they come back to the ground and were inspected, we've seen the little pits taken out of the windows. And they could have small little pieces, whether it's even flicks of paint, have caused that type of damage because of the relative velocities are so great.
Right.
And so even a tiny thing with just a little bit of mass can cause major damage. So if you have a lot of these satellites over time, let's say tens and thousands of them that are being put up into Earth orbit, every one of these launches causing this shedding of some debris, some amount of debris. And it seems like we can't launch things without shedding a little bit of stuff. I mean, that happens just by
That happens just by wear and tear.
yes, the name of the game in some sense. It's going to happen. Then that means over time that stuff will build up. Now some of it will re-enter. It's in low enough orbit that it will come down within a certain period of time, on the order of, depending on how low it is, could be on the order of even hours if it's low enough. It could be on the order of days, weeks, months, or even years. But you can imagine that we put up so many satellites, which is some of the proposals. It's not just one company. There are multiple companies that are doing this sort of thing or wishing to do this. There are multiple countries that are wishing to do this or if not, are in the process of doing it right now. And so over time, there can be a scenario in which there are just so much debris, if you like, that's in orbit around the Earth, that it would be unsafe for a single manned launch from the surface of the Earth. That is, that you could launch, let's say, on a trip to the moon, but there is a real probability
that
a collision will occur because there's just so much stuff. There's no timing that you can do. At any time that you launch, there's almost a 100% chance of an impact. Right. That's kind of taking it to the limit, obviously, right? Extrapolating into the future, if we keep sort of increasing at an ever faster rate the number of things that we're putting in orbit.
Right.
And so it could get to the point where we can't do any type of manned human space flight because it is unsafe given the debris we have to fly through.
Right.
So then we'd have to shut down the human space exploration part of things.
And governments, I know from some panels that I've been in at conferences, that the governments are starting to talk about this. And it's why people get upset right now when China, the US, or Russia flex their muscles and shoot down a satellite. What they're basically doing is throwing a bunch of debris in the path of the satellite to create more debris.
Yeah. In fact, you can, I'm sure, do an historical sort of search to see how many times the International Space Station had to dodge. And that's just going to become increasing occurrence as we go forward in the future.
Yep.
So that's the problem. That's the issue in all of this, is that it would make the space environment, or near Earth environment, so dirty that you can't launch.
Right. But I think we'll end up getting a handle on that. We're clever critters. We'll figure out some way of getting that junk out of orbit, or at least enough of it that we can keep going to orbit.
Right.
But I also think we're just going to keep putting more and more satellites up, active satellites up there. So,
yeah. Well, I mean, there are several companies around the world that are actively looking at this business of cleaning up a lot of this debris.
A lot of it is international law and laws about piracy, because if it's not yours or your country's equipment up there, taking hold of it, even if it's dead, is considered piracy.
Well, I wonder if you were in the middle of nowhere, let's say the middle of the Pacific Ocean, and there is a bottle floating in the ocean, and you would classify that as litter.
Right.
And you pick it up, and it has writing on it to indicate the country of origin. Are you a pirate now because you've taken that from the ocean?
That's the attitude a lot of people are taking, is this is dead junk. Get it out of there.
Right.
Who cares who does it or why? And what some of these countries, the US and Russia and China, are afraid of, though, is that one of these dead satellites will actually be, intelligence piece, and now they'll get a look at what we were doing and how we were doing it and what we were looking at. But that's a whole different, that's not in the scope.
Well, I mean, it's interesting even to try to figure out how do you capture something that's traveling at 5 miles per second.
Right.
That's the interesting thing in that. And so, I mean, so getting on to the discussion about the impact of the satellites on telescopic observations, from the ground base, we're told that if you should have your telescopes in space anyways.
Right.
You'll get a better view of the universe just because you don't have to see through the blurring effect of the Earth's atmosphere. And of course, the Earth's atmosphere blocks a lot of the electromagnetic radiation from even reaching the surface of the Earth.
Right.
For example, if you're looking or interested in observing X-rays coming from astronomical sources, you can't have that telescope on the ground setting.
Right.
because it won't observe any X-rays coming from space. It gets blocked totally by the atmosphere. So those type of telescopes have to be in space.
Right.
Now, for the Hubble itself, or let's say the future generation of those type of telescopes, yeah, what you're looking at is putting them into an orbit that is above the satellites.
Right.
So, and then it's a matter of, well, you can think in the future, the space between, the cislunar space, which is the space between Earth and the Moon, is probably going to become crowded if we end up building bases on the Moon itself. There's going to be a lot of transport back and forth to the Moon. There are going to be a lot of communication satellites in orbit around the Moon and so on. Eventually, we're going to have to put our telescopes beyond the Moon.
Right.
And so we're going to get pushed further and further and further away from the Earth.
Which increases the cost and increases the difficulty and increases. Is it an answer? Yes. So yes, the answer, Wonder Goon, is yes. Well, the Hubble can't be moved to a higher orbit to avoid satellites and debris, but we can move space telescopes to a higher orbit.
I mean, there's
there's a limit.
Well, there's no reason we couldn't move the Hubble. I mean, you could strap on a rocket. I mean, there's talk now, like SpaceX and NASA are in doing this study to see if SpaceX can fly up to the Hubble, repair it, like that is to replace some of the gyroscopes and so on, do some maintenance, boost it into a slightly higher orbit so it's more stable, sort of things that the shuttle repair missions had done during that program. Right. But there's no talk, of course, of boosting it in a huge orbit really far away. And that would impact, I'm sure, some of the communications and stuff that's available. It would be harder to communicate with us further away. It wasn't designed to be that far away. But if you had the right equipment, like you build a new telescope from scratch on the ground whose purpose was to be far away, like the James Webb Space Telescope, that is far away from the Earth. I mean, something like that would be useful. And that's probably what's going to happen in the future. But it still doesn't eliminate this problem we're going to have with all the orbital debris.
Right.
And the hazard it'll have for human spaceflight. And that's something we're going to have to definitely deal with in the future. But like as I mentioned before, it's interesting, some of these companies are looking at how do you collect a particle, let's say a bolt, right? That's 2 inches long, let's say, 1/4 of an inch wide. And it's traveling 5 miles per second. Are you going to catch it in a baseball glove?
That's a little pepper on it.
How do you do that, right?
Right.
Now, have captured fast-moving particles before. You might recall the Stardust mission where we collect particles from comets and so on.
Yeah.
And so in that case, we used aerogel. So this material that was extremely light had a lot of very low density, a lot of pockets of air built within it. And the material essentially traveled through a fairly lengthy track in the material before it slowed down and finally stopped. And one of the reasons of doing that is we didn't want to pulverize that material.
Right.
Right? It's not like you wanted to slam into a steel wall or something.
So what you're saying is we may actually use a catcher's mitt.
Yes, a specially designed one. Something that we couldn't use in baseball because that would slow down the game, waiting for it to be captured and then cleaning all the gel off of the baseball, or you have to use a new one each time you caught it. But yeah, we can design technology, right? Human beings, obviously, we are thinking creatures, and it's amazing some of the ideas that we're able to come up with.
Present us with a problem, we're usually capable of coming up with a solution.
But in all of this, it's going to take a lot of money, like normal.
Right.
And it's going to take a lot of work effort to do this.
Right.
And essentially, it's pollution.
It's right.
That's essentially what it's litter, and we want to think of it that way, right?
It's junk.
So this is going to be probably more of an issue. In fact, almost with certainty, it's going to be more of an issue as the years go by. So this is something we're going to hear more and more often is these kind of effects that you see in these images from the Hubble Space Telescope.
Yep.
So it's not going to go away in any sort of near-term type of situation here. So
that's kind of where I'm thinking.
Yeah.
So,
but one of the reasons why we have telescopes in space, and there are many different types of telescopes. We know the Hubble Space Telescope is arguably probably the most famous telescope all of history. At least it has been. The James Webb, I'm sure it's
will be right up there with it.
Will be right up there with it, if not already. And there are different other telescopes that we can put in space, but the sole purpose is really to get a much better view of the universe.
Right.
Get above the disturbing effect of the atmosphere. And from that, we can get a good handle on such problems as how do stars form?
Right.
Where do stars come from as part of that? What happens to stars? Do they live forever? Do they have finite ages? What happens?
How
Do
do they
stars
grow old and die?
Yeah, do stars die? And what does it mean to die as a star? So all of that is wrapped up in this sort of broad heading that we call stellar evolution.
Absolutely.
So Robert, do you want to tell us a little bit about stellar evolution?
Sure. I even studied up on this topic today. Stellar evolution is doing just exactly that. It's looking at how stars form, how they age. So how do they go from just a cloud of molecular gas and dust? And that's not just any cloud of dust that'll happen. It's going to be cold enough that gravity can take over and make it start collapsing in on itself. And it's got to do it in such a way that it doesn't heat back up, because what happens when you compress a gas? It heats up. And if it heats up too much, it blows itself back apart. So it's got to come together just right, slowly but surely, and then eventually you get a hot enough, dense enough core that fusion can happen.
Right.
That hydrogen atoms, protons, can start sticking together.
So I just want to entertain this idea. So way back, so this is, for those of us who are old, this is back to an earlier point in our lives, if you like, back, I would say, let's say in the 1970s.
Mm-hmm.
Okay. So back in the times when computers are starting to get developed where you can actually use them, like they became cheap enough,
right,
where the average sort of professors would have access to computers, rather than just the government, like the military or a special way that they would have the computers at that time. So when they got cheap enough that people started to use these computers, not necessarily the individual at home, but people who are in these scientific type of enterprises.
mm-hmm.
One of the things they did in terms of understanding stellar evolution is try to input all of the known laws of physics and see if they can take material, so let's say gas and dust, and get that to collapse under gravity and form a star. And in the early attempts to do that, it's interesting to note that they could never get a star to form.
Couldn't do it.
Right. And then you write a paper, here's the joke, right? That you do this simulation with your computer, you put in all the known laws of physics, all of the initial conditions that you expect for that would start off, eventually form a star, and then you try it in your simulation and you run multiple simulations, and every time you run a simulation, the object would never collapse to the point where you would form a star. So then you write a paper saying stars don't exist. That's the joke, right?
Right.
And so the obvious problem in all of that, in terms of star formation, was we could never get the object down to the point where it would allow nuclear fusion to occur.
Right.
And it was really understanding in a better way what are those initial conditions that we need to reach before ultimately something turns into a star.
Right.
And you need to start with something that's already fairly dense but very cold. That's the key.
But very cold.
So
yes. And so that's how you get a star, is you have to have this cold gas, because we can look out and we see nebulae everywhere in the universe, and all of these are gas and dust clouds. Why don't they all collapse to become stars? Because they're too hot. They've got stars nearby lighting them up. That's why we see them. So they're too hot. So that's one of the things. So getting a star is actually a pretty interesting process in the first place, because it just doesn't happen with everything that's out there. So then we get into looking at, you've heard us mention it, the HR diagram, or the Hertzsprung-Russell diagram. And this is our model for how stars evolve and everything. And so here's a nice little simple graphic about it from the ESO, the European Southern Observatory. And you can see that there's this path running diagonally across the middle of the graph. This is called the main sequence. Once a star is born, once it starts fusing hydrogen in its core into helium, it moves on to this main sequence. So you can think of the main sequence as being adult, fully formed stars. They're, put in terms of human life, they're 18 to into their 40s probably. They're fusing hydrogen into helium. They're happy. They're fairly stable. Put that in quotes.
no.
No, we haven't known him. I'm sorry.
know.
Ms. Schwalm has asked, I understand our former student Kurt Cruz is a space junk expert. Have you known him? So the answer is no on that. So getting back, what happens though is that as the star runs out of hydrogen in its core, it can no longer get energy because there's not enough hydrogen there. And so the core collapses. Oh, do notice that our sun is marked on there. It's a nice, fairly low mass star in the yellow region of that graph.
In the main sequence.
Main sequence.
Yeah.
Yep.
So what's happening inside the core of our sun then?
Well, it's fusing hydrogen to helium.
Right. And how do we know that for sure?
How do we know that for sure? Well, because if it was coal or any kind of fire, it would have run out of fuel by now. But given its energy output, energy output for 1 year would have to be more massive than the star is. Other things are we have evidence from now neutrinos.
Then bingo. Right? Because you could argue, right, if you wanted to play devil's advocate, you could say that some type of other nuclear process that's occurring.
Okay. But yeah,
Right.
we've detected neutrinos now, and we've detected the quote-unquote solar neutrinos. So we know what type of reaction produces those types of neutrinos.
Right. So the byproduct of the fusion of hydrogen and helium we can detect here on Earth,
Right.
which proves then there is this nuclear fusion reaction of hydrogen and helium that's occurring in the core of our sun.
Right.
Now, what sort of temperatures, Robert, are we talking about that allow this type of fusion reactions to occur?
I don't remember the exact, but it's on the order of 10 million.
Yeah, so anything greater than 10 million will
Right.
support that hydrogen fusion. Now, do you remember what is the core temperature of our sun?
I don't remember. 11 million, 12 million?
16 million,
16
roughly.
million. Okay.
Okay. Now, how do we know that number? Because people always speculate. How do we know what we know?
Okay.
Right. So, who was the person? Right. What was his name? So I can go to his gravesite or at least the memorial for him. That actually took a thermometer and put it at the center of the sun, and then radioed back what the temperature was, in his last dying breath. You see what I'm getting at?
Yeah. And the answer is our thermometer has to be mathematical theory and then observable evidence that from particle colliders that these things happen.
So what's one way we can determine the temperature fairly precisely of the center of the sun? We note what? And we just talked about it.
We note the surface temperature. We notice the neutrinos. We
The
notice
neutrinos.
Okay.
So the reactions are very sensitive to temperature.
Right.
The rate of the reactions, right?
Right.
So if you crank up the core temperature just a little bit, you get a larger number of influx of neutrinos.
Right.
If you lower it,
You get
right,
less.
you get less neutrinos coming per second, let's say, arriving at the Earth. So by actually measuring the neutrinos coming from the sun, we can get a fairly decent measurement of what is the temperature of the core of the sun.
Okay. I knew they'd done it. I knew they had observational evidence, but I thought it was still from working out what's called the gamma peak of what's the right temperature to get the most.
Right. So we
Energy
actually
out.
get because of the high dependence of temperature on those nuclear reaction rates, we can get a fairly decent measurement of that core temperature. In fact, we don't have to sacrifice anybody. We don't
Right.
have to send anybody there with a thermometer.
Although we have sacrificed or in the process of sacrificing a probe that's around the sun called the Parker Space
Solar probe.
Probe.
Yes.
And it is actually, at its closest approach, is dipping into the outer layers of the atmosphere of the sun, the corona.
Yes.
So it's got some pretty good ablative armor that is on its front end as it dips down into that close. But it's taking some good thermometer gravimetric readings and everything. So
Now, getting back
to stellar evolution.
So are every star that we see in the sky exactly like our sun, Robert?
Absolutely not. Some are higher mass, some are lower mass.
So where do they fall on this HR diagram that you
let's
showed
go back
us?
to it. So the higher the mass of the star, the hotter it has to be because it has to burn and produce more energy. It has to produce a higher flux to counter gravity trying to crunch it down. And here I am gesturing again when you can't see me. So because it's hotter, high temperatures produce bluer light. So those stars are going to appear whiter or bluer than our sun does. Similarly, if it's smaller mass, it does not have to produce energy at quite the rate because it's not being crunched by gravity as hard. So it can stay cooler. And so cooler means it's producing redder light. You can think of this, if you've ever had a fireplace and you've stuck the poker into the fire, it starts out eventually, you can see it start to glow nice and red. And if you leave it there long enough against the good hot coals, it'll start turning yellow and then white. And it's because the hotter it gets, the bluer, the more the peak wavelength given moves to the blue end. So this upper left is where we have blue stars, large, heavy, high mass blue stars on the HR diagram, and along the main sequence. They're still fusing hydrogen into helium. They're just doing it at a much higher rate to counter the greater crunch due to gravity.
So is it fair to say that the main sequence is really a mass sequence?
It is fair to say that. It is a mass sequence.
And so where would the lowest mass stars be on the main sequence in this diagram?
They should be down in the lower right-hand corner.
So the bottom
where it's
right.
red.
Right, so as you go up from the bottom right to the upper left, you're going to increasing mass as you make your way up the main sequence.
Increasing temperature and increasing brightness.
Now, just out of sake of numbers, and I'm going to test your skill here.
Oh, Lordy.
Ready? Do you remember or recall the mass of the sun?
10 to the 33rd grams per grams.
Right, so it's about 2 times 10 to the 30 kilograms.
Right.
Or about a little over 330,000 times the mass of the Earth. Now, what about the size of the sun? In terms of the Earth, that's kind of an easier number to think about.
That I don't know. I know it's about 600,000 kilometers, I think it is, radius.
So it's about 109 times the size of the Earth.
Right.
So that gives just kind of a perspective of the size of the sun itself. And that is not the largest star.
By any stretch.
By any stretch.
And what I like to point out is the Greeks actually got an estimate of that size once upon a time because they started using the lunar shadow angle and so forth, that they used simple geometry to calculate how far away the moon was in Earth radii. And then they figured out that the sun had to be that many more. They were wrong, but the fact that they weren't understood enough to use geometry to actually go that route is something that I like pointing out and backs up my claim. We're clever critters. We see a problem, we figure out a way of doing it if we really think about it and want to.
Right. But if we knew the size of the sun, how would you use that to figure out its distance?
If you know the size of the sun, you can figure out the angle subtended by that size and figure out the distance from
That's
that.
right. So if you had a good estimate of the size, or you can turn it around, if you had a good estimate of the distance,
you can determine the size.
From the angle
Yep.
that the sun makes, the apparent size.
Absolutely. And that's what I was saying. They were using the shadow angle of the moon to
Right.
figure out how far away it is. And that also then gave them an estimate of how large it was. And then they used that. They knew at a solar eclipse, the moon covered the sun. Well, they can't be at the same distance. So.
Right. And so the way it would work in our everyday life, and we don't even really think about it, is if you watch somebody walking away from you,
Mm-hmm.
and if you note that they're a certain angular size that they appear to be, and if you double the distance to you, so you wait till they double the distance they're walking away, then they're going to be half that size.
Half the size.
And we can use that correlation to determine
Yep.
then the relationship between the angular size of things based on their real physical size and how far away they are.
Right.
Yeah.
So, getting back to the HR diagram.
Now,
this is the
what?
revolution.
So,
Go ahead.
so Rob, what are the largest stars? Not necessarily main sequence stars, but what are the largest stars in the universe?
The largest are in that band up at the top, very top, that says supergiants.
And how do they get there?
Okay.
What's the track?
The main sequence, as the star begins to run out of hydrogen in its core to fuse, it stops being able to produce as much energy, so the core collapses. Well, that makes it get hotter, which means the outer layers are now heated from inside. They expand and cool.
So let me interrupt you here,
So,
in case
yes.
somebody's wondering. Why don't stars live forever?
Because they've only got a certain amount of energy. It's like the difference between an SUV and a Prius. The SUV has a bigger gas tank. Usually most of those got around a 20 or 30 gallon gas tank. But it takes a lot more fuel to move the SUV than it does the Prius. So it burns through its fuel a lot faster. And the smaller car may have a smaller tank, but it also doesn't burn the fuel as fast. So,
Right. So you could say the ultimate reason why a star doesn't last forever is because it has a finite amount of fuel. It has a full gas tank at the beginning, but nobody's coming along to fill it back up.
Top it off.
Right?
Exactly.
Now, you could argue there are these rare things that could happen, but they're very rare, where you can top up that fuel tank. And what are some of the things I'm thinking about here, Robert?
You can have stellar mergers. If they're in a binary, they can be so close that they eventually spiral and fall into each other, usually because their outer envelopes, their atmospheres, are interacting. Because unlike black holes, they don't radiate enough gravitational energy to... Anyway, that's a whole other topic. So if they merge like that, they both use some of their fuel just getting to that point. But now they've kind of refreshed each other due to the mixing that occurs as they merge.
Right, and we'll actually see that in some of the stuff you're going to show later, right?
Right.
That sort of case. So
Yep.
we'll talk about that when we get there, I guess.
Okay.
Okay.
So going back to that HR, so as these massive, huge stars at the upper left-hand corner of the main sequence start to move off, they swell because the core is getting hotter, but that makes the outer envelope expand. It gets cooler, but they get larger, so they get brighter. A whole lot of complicated interconnections there, and they become supergiants.
Right, so we have this shell burning that takes place outside of the inert
Because the core
helium.
is now so compact and so hot,
Yeah.
it actually gets hot enough for the core to start fusing helium into oxygen and carbon. And then if it's massive enough, it'll fuse the carbon and oxygen into silicon and magnesium. And if it's heavy enough, that'll continue on until it gets to iron. More on that in a moment. But because that core is so hot, the outer shells that are immediately around it start being able to fuse materials as well. So you end up with what we call an onion model, where around the core there are layers of hydrogen fusing into helium and helium fusing into carbon and oxygen, and and you get the picture. And so in the very center is this iron building up, but on the outer rim, it's fusing other elements.
And that's only for the high mass star.
That's only for the really high. Smart star like our sun, it should be able to undergo helium fusion in its core when it starts to die, and that's what it moves off to this little nub that's labeled giants. And so, but it's not heavy enough, not massive enough that it shouldn't really start being able to fuse then the oxygen and the carbon into heavier elements. And so the sun will die. So hypothetically, what would happen to a planet in the habitable zone of two stars that merge? Would the habitable zone apparently change or move to where the planet isn't in that zone? Yes. The planets would almost certainly be thrown, their orbits would become chaotic for at least a time if they aren't thrown out or engulfed into the star. But if they weren't, it would definitely change the habitable zone because the star has gone from two stars at the center to one massive star at the center.
Yeah, so it would depend exactly where that planet was orbiting. So if the orbit of the planet was far away from the two stars, so you can imagine a situation where two stars are orbiting each other, the planet is much further away. As the planet orbits those two stars, it's as if those two stars is 1 point mass at the center of the foci
Right.
of the orbit, as we say. So it wouldn't affect the planetary orbit that way because you're assuming there's no mass loss as the two
Fair
stars
point.
merged,
Fair
right?
point.
But the star itself, that is the result of the merger, its structure would adjust. So it would have a certain amount of luminosity and surface temperature and so on. And so that will change, therefore, the amount of energy that's output by that one single star.
Right. And so,
And that would affect the habitable zone
right.
at that
In
point.
the end, yes, it could go from being in the habitable zone to being outside of it relatively easily.
Right. Now, if the planet was actually orbiting one of the stars, not
Then it-
both, then when those stars were, that planet would get destroyed, would be vaporized, would become part of the single star that would exist after the two stars merged.
Yep.
So it all depends on the details of where that planet actually is.
Indeed.
Yeah.
So, the last thing I'll bring up about this HR diagram, I've got some more, is that low mass stars, when they finish dying, they puff off their outer envelopes. All that's left is a bright, hot core that can't fuse any energy, but it's hot. And space is not a good radiator of heat. So you form essentially a stellar core that's now exposed to space, and that's what we call a white dwarf.
Right, so the star goes through this period where it's called a planetary nebula.
Right.
So as the outer atmosphere get ejected into space, they become unstable. They gain enough energy that they reach what we call escape velocity, which is something we talked at length about in a previous podcast related to black holes. And that material is forever moving away from the very central leftover core of that star. And so that material then spreads out, becomes more diffuse over time. And as it gets further away from the heat source in the center, that gets dimmer and dimmer, eventually fades out.
Right.
And then presumably new stars can form from that debris.
From that material, right.
But the core region left over, that would be a white dwarf. In fact, that's the end state of our sun, right?
Yep.
It'll turn into a white dwarf and basically just cool down to the background temperature of outer space.
Right.
Now, here's one for you, Robert.
Okay.
What is that background temperature of outer space presently, approximately?
3.7 Kelvin?
2.7.
2.7. Okay.
Yeah, very good. Pretty close.
The cosmic microwave background, folks. That sets the temperature.
That's right.
So
So it's around 3 Kelvin, if you want to round it off to a whole number.
real close to absolute zero, but not quite there.
Yeah.
But, this is a nice cartoon. This is a nice HR diagram that shows you all these parts, and it looks real neat and everything.
Do you want to, before we move away,
before we move away
we
from
should
it.
talk about the label, what's actually drawn here for the
Oh,
labels.
okay. So the
Should have
label
done that, I guess.
should have done that at the beginning. The vertical axis, the up and down axis, is luminosity, brightness. So, in other words, these blue stars up at the top are much brighter. But again, they're burning more fuel. They're burning it faster. It makes sense that they'd be outputting more energy. They'd be brighter.
Right. So we're brighter, so we need to, just to clarify a thing here.
Okay.
How something looks in terms of brightness depends not only on its intrinsic brightness, but also on distance,
On
right?
its distance.
So luminosity is a measurement
Of the actual output of the star.
the energy output, the intrinsic
Yes,
brightness.
The intrinsic brightness.
Right.
Thank you. That's the word.
Okay.
So, yeah, it's not how bright it looks to you in the night sky. It's how bright it really is that we're talking about. And then along the x-axis, the lower, the left or right axis is surface temperature. And they're also usually often done in spectral, what we call spectral type, which is the O, B, A, G, F, K, M, going from left to right. So the left-hand side is hotter, and as you go up, it's brighter. So the top of the left of the main sequence is hot and bright stars, and the lower right, where the main sequence tails off, is cool and low brightness.
Right, so you'd be hot and bright stars in the upper left and massive stars.
And massive.
Right?
Yes.
And the low mass ones. Yeah. So when we say in terms of mass, how does that affect life expectancy? Do you want to get into that kind of?
That's one thing I didn't study up on, so I can't give exact answers. But basically, the high mass stars on the main sequence for on the order of around 1 million years.
The most massive ones, yes.
Okay, whereas the ones down on that lower right side, those M dwarfs as we call them, can last 1 trillion years.
Yeah, the least massive ones up to 1 trillion years.
And it has to do with a lot of factors. I'm not going to try to go into, this is not an astronomy course. That's not why you're here. But we kind of want to get into some of the little details.
Well, then thinking about the life expectancy of these stars, the first generation of stars that form after the universe was created in the Big Bang, as far as we can tell, right, our best sort
Should
of
have
ideas
been
that we have.
truly massive.
Well, if we have any low mass stars that formed,
They'd still be here.
they'd still be living today because the
Right.
universe is about 14 billion years old. So anything that had a very low mass could easily have a life expectancy exceeding 14 billion and therefore is happily on the main sequence
Still today.
today,
Yes,
converting hydrogen into helium in its core.
right. While the truly massive ones, they've been gone for a long time.
Right.
Long time.
And we know that's the case because we are the result
Of
these high mass stars that have lived their lives.
Remember that onion skin model? All of the iron in your cast iron skillet came from the core of a star.
Yes, the iron in your blood.
The iron in your blood from the core of a star. The carbon that makes up your DNA and cell structures came from the center of a star.
That's right. So after the universe began, the most things that were around in terms of normal matter was essentially hydrogen and helium.
Right.
A trace amount of lithium, beryllium, this kind of
Some
stuff.
boron,
But just
minuscule.
a very negligible amount. But everything essentially you see in the periodic table beyond hydrogen and helium were produced inside of stars.
Right.
And so for us to contain those atoms beyond hydrogen and helium, and the Earth to contain those atoms beyond hydrogen and helium, there must have been past generation of stars that formed, lived their lives, and then died. We wouldn't be here today if it wasn't for the fact that stars have died.
Right. You got it. Absolutely. Which I think is just a neat thing. I love, I think it was Carl Sagan who first said it. You were stardust.
Yeah, I mean, we're intimately connected with the cosmos.
There you go. So
that gives you a reason not to turn blinders towards the cosmos, what happens beyond the Earth, right? Some people say, I don't care, I'm more interested in what's going on Earth. We are part of the universe. You can't get away from it.
From that.
We wouldn't be here if it wasn't for the universe itself.
Yep.
So that's a motivation factor, and maybe we should try to understand as much as we can about that universe, because that's our history.
That's our history. That's our future.
Yes.
Yeah.
And it's all tied together.
Absolutely. So how about we look at what a real
HR diagram?
HR diagram looks like? I've got
Sounds
examples
good.
of two. This one is from a space telescope named Gaia that's run by the ESA, the European Space Agency. This is from the download from their second data set. And it's basically plotting 4 million stars within 5,000 light years of Earth. So these are all stars in our galaxy, and relatively speaking, within our neighborhood of the galaxy. And again, you can see that main sequence going from the upper left down to the bottom right. It's much broader, though, than our cartoon was. You can also see this labeled giant branch where stars are beginning to turn off, because that's the actual the turn off, and they're going up onto the giant branch, and that's where stars are starting to die.
Right, so when we leave the main sequence, at that point, that's when all of the hydrogen in the core of the stars has been converted into helium.
Right.
And so because you lose that pressure support once the hydrogen fusion shuts off, then something has to change at that point. It's no longer in a balanced situation.
It's unstable. And that's some of the breadth of these bars going off in various ways, these branches, is because it's not a stable process anymore.
Yeah,
the main sequence.
So in that giant branch, then what's happening is in the very center is you made up of essentially is an inert core of helium. Mm-hmm. And that core is shrinking in size. It's getting smaller, it's getting more dense, it's getting hotter. It gets so hot. In fact, the hydrogen, so stars are mainly composed of hydrogen, the hydrogen that immediately surrounds the core has reached the temperature now in excess of 10 million Kelvin and is now able to convert hydrogen into helium in a shell surrounding the core. So that shell burning process then causes the outer layers of the star to start to expand outwards.
Right. And then the helium kicks off. But helium doesn't fuse smoothly like hydrogen does, so it tends to do it in pulses. And that's why, again, those giant branch stars and upper and right, the supergiants, they're unstable. They pulse.
Now, notice on the diagram, Robert, there's a sort of a little bit of a increased density in objects.
Right.
On your scale here, on the vertical axis, it's around a little bit of between 5 and 0, but it's above 5, so somewhere around 4, I guess, 4.5. Do you want to explain what those objects are? And it's right on the extreme left then of the diagram.
On the extreme left?
Yeah, this area.
Oh, actually, I don't know what those are.
Well, what are some of the things we talked about recently?
Well, you got neutron stars that can form. You've got black holes and black hole mergers. You've got supernovae.
When you merge stars?
Oh, the blue stragglers.
Yes.
That's what you were aiming for.
Yeah.
Yeah, so you've got some star mergers. The point I'm trying to make is the real thing looks a bit more messy. Right. It's still showing the same things, but yes, it looks messier.
So if that location is of merged stars, that just gives you an idea how relatively rare that situation is.
Right. Oh, okay, I see what you're saying. Yes.
Right.
There's just that little bitty tiny block of
Clump.
right there by the 5 on the vertical axis on
Right.
the left. And it's just a tiny clump. So out of 4 billion, there's just enough to notice that there's even a group there.
Yeah.
And then we got the white dwarf blob down there at the lower left. And you can see that there's a wide range of temperatures and brightnesses for them. Now, one thing I will ask you then, why is there that broadening towards the lower right, but not quite the lowest right on the main sequence?
Oh, on the main sequence itself?
Yeah,
Yeah,
it's
so,
thickening.
so some of that I think is due to rotation effects too. So some of these stars are rapid rotators, and that will change slightly their luminosity and their measured
Right.
surface temperatures.
And there are other factors.
And there are
as well,
competing effects, and there's differences in metallicity and all these other things
Right.
that can possibly make it more complicated. So these higher order effects that can occur.
but can occur. And, again, we could teach a whole class on this because they do teach whole classes on this. Okay, so I'm going to show you one more HR diagram. This one I don't have to do an attribution for because this one was created by me. It looks really messy because there's a lower line that you see across the bottom that's cut off. I couldn't see anything dimmer than that.
That's the horizontal line.
That's the horizontal red line. Then there's effects of what we call reddening due to the fact that there's gas and dust in between us and those stars, and that's that red arrow pointing kind of diagonally at the bottom left.
So you want to explain what the axes are then?
Oh, the axes. This is a HR diagram developed from what it's called a color diagram. So along the vertical axis is what we call the V-band magnitude. I was looking through a particular broadband filter to get how bright it was through that filter.
So this is apparent brightness.
So this is an apparent brightness. And then across the bottom, I took that V magnitude, V brightness, and subtracted another filter's brightness called the I filter. So it's V minus I. That's why it's down there at the bottom.
So I is roughly in the red,
Is
and
in-
V is sort of halfway between blue and red. Visual.
Right, it's in
band.
green.
Right. So what you're seeing on the bottom really then is color.
Is a color.
Is a color.
Yes. And the V band on the vertical is a brightness.
So that's why we call it the color magnitude diagram.
You got it. But in the end, it's an HR diagram because you can see that there's this diagonal strip down the middle. It gets broader as it gets to the bottom, probably because I was including stars not actually part of the cluster that I was looking at.
So what's this target then that you have plotted here?
This was the Hyades. This was,
okay, so this is what we call an open star
Open
cluster.
cluster. And so I probably had some targets that I said were part of the cluster that were really not. And that's some of the broadening of that main sequence band. But most importantly, up at the top, you can see where it kind of Y's out, that there's a branch off of the top. What I was doing this for was to get an age for the cluster. And it turns out it's about 1 million, 2 million years old. So
that branching out that you see, that goes off to the right a bit, and a little bit up to the upper right. So that's the turnoff.
that's the turnoff.
Okay.
That's what we were trying to measure.
So do you want to specify exactly what we mean by the turnoff?
Okay, let me come back so you can see us because I want to gesture. Okay, so at the top of my graph, it's like this, and off to the left, going to the right, was this branch off, this turn off. And so all of these stars are on the main sequence, but these massive ones have started to peel off and head towards the supergiant.
Now, why do they peel off?
Again, because they've stopped fusing hydrogen in the core has collapsed, heated up, shell burning has happened around. This causes the outer layers to expand.
So in other words, they've run out of hydrogen in the core.
They've run out of hydrogen in the core, yes.
Right. Okay. And then things must change because when a star is on the main sequence and happily converting hydrogen to helium, then there's this balance of the internal pressure pushing out, that pressure generated by the fusion, and gravity trying to
push it
collapse
in.
the object, making it smaller.
It's a tightrope walk, folks.
Yeah. Do you know the fancy term we use for that type of balance? Do you remember? Terminology.
Hydrostatic equilibrium.
Exactly. Hydrostatic equilibrium. So there's a fancy term for it if you want to tell all your friends and family.
To a degree, you are in hydrostatic equilibrium because
Right.
you're not bursting into flame, but you're also not keeling over, shivering because you've lost too much heat.
Right.
So it's kind of the same thing. Different processes involved. You don't fuse hydrogen into helium, but it's a similar idea, actually. So where does all that energy come from? And that's this nice little chart. This is called the binding energy per nucleon chart. And basically, down here at the lower left, where that red line starts, is where hydrogen sits. So hydrogen has very little energy per proton because it's a proton. But when we fuse it to get helium and we move up that red line, and as far up as we move, and when we get up here to about 4 nucleons, that's how much energy we've gained. Okay? And going from hydrogen to helium. Well, you can kind of see that it tails off. You start getting less and less as you move up the line. So fusing helium into the carbon and oxygen does not give as much energy as the initial fusing of hydrogen into helium gave you. So you have to burn it faster. You have to burn it harder. You go through it quicker. This is also why helium burning is not stable. It flashes, it pulses. So this can continue up until we get to the top of this chart where iron is labeled. Everything in the universe wants to be iron. Iron is the bottom of the hill, or in this case, the top of the hill, but we usually show this graph. I couldn't find one, but it's usually turned over. And iron is shown as the bottom of the hill because everything wants to be the iron. It is the most tightly bound. It is the most stable of all of the elements. So this is also why we say a star that starts fusing iron starts appearing in its core, the star is dead. It's doomed because iron starts absorbing energy, starts absorbing heat, and instead of being able to use that heat then to fuse other elements, it starts going into the iron.
Right. So the way thinking about it is, as you start with the light elements and fuse them together, that reaction in chemistry, we would say that's an exothermic reaction,
Right.
The net release of energy. And then by the time we reach to iron, then to fuse iron into something heavier requires energy. So that would be an endothermic reaction.
Right.
So that would be in that energy has to go into the reaction rather than being released. And we want that energy to be released to support the star from collapsing in on itself, essentially due to gravity. Because anytime you have mass, you have gravity. So gravity's always there. And there's this constant battle between gravity trying to make things smaller and this internal pressure pushing outwards, counterbalancing gravity.
Right.
So if you upset that balance, then things have got to change. And because there's a finite supply of fuel in these reactions, then things need to change throughout the lifetime or lifespan of a star. Now, Robert, I always, some people might wonder, for example, when we talk about a simple hydrogen atom, in that case, the most abundant form of hydrogen is a single proton in the center of the atom, and then an electron, you can think of it as on the outside of the nucleus. And we're not going to get into the actual model of the reality that you think of where the electron appears, but let's use an old model that we know is incorrect, called the planetary model of the hydrogen atom.
Okay.
And think of the electron as just orbiting the center of the hydrogen atom like a planet going around the sun. Like I said, that's a wrong model, but let's just use that simplicity to our advantage now. If we think of a planet going around the sun, we say the planet is held in orbit around the sun because of the force of gravity.
Right.
Now, for the hydrogen atom, because we're dealing with things that have very, very little mass, the gravitational force of attraction between a proton and electron is essentially negligible. So what holds the electron in orbit around the proton is not gravity, it's the electric force.
Electric force.
And why it's an attractive force is because the electron and the proton have opposite electric charges, right? The electron is negative charge, the proton is positive charge. Unlike charges attract, like charges repel. Okay?
Right.
Now, when we think of taking that very simple and wrong model, but let's go with it here, then going up to the next stage, which is helium, right? In that case, ignoring the neutrons that are in the center of the helium atom, just think of the protons. There are 2 protons in the center of the helium atom, and the most abundant form with all of the electrons is 2 electrons that would orbit the outside of that nucleus for the helium atom. Now, the problem that we have when you first kind of think about this stuff is I can understand the electrical force of attraction between the electron and the proton, but how do you get 2 protons to be near each other in the nucleus of a helium atom?
In fact, I saw somebody recently commenting on the amount of force that those two protons are trying to blow themselves apart with. And it's 300 newtons. In other words, it's able to launch a labradoodle.
Right.
That's how they put it. They put it in launching labradoodles.
Right, so because the 2 protons are positively charged and they reside close to each other in the nucleus of the helium atom, there must be something other than the electric force at play here. And that other something is the strong nuclear force. And the way to think about it, very simple cartoon type terms, is imagine you have 2 hooks. A hook is attached to a ball. And if you bring those balls close enough that the hooks engage, then you can't pull them apart.
Right.
And that's kind of what's happening here. If you get them close enough, the strong force overwhelms the electric force of repulsion in that case, and able to bind those protons together.
Right. And that releases energy, which is what fusion is all about, up until you get to iron. And then you've got to put energy in to bring in that, because again, the electric force is now building. And it's a nasty process.
Right, and that kind of explains why we try to make hydrogen fusion in a laboratory that ultimately would supply all of this clean, free energy to the world. Wow. It's a very difficult thing because it's hard to get 2 protons very close together to allow these type of nuclear reactions to occur in a laboratory situation.
But at the same time, we can see from this red line, going from hydrogen to helium produces a lot more energy than splitting uranium out here on the far right end of that line into products here at that. But we're running out of time.
So we can definitely pick this up in a future podcast.
Absolutely.
Okay. So just to finish up today, so I just want to mention, first of all, that our next podcast will actually be Tuesday, March the 21st. So for us here at the University of North Dakota, next week is our spring break. And so we're not going to do a podcast live on next Tuesday. So the next one will be on March the 21st at 3 p.m. Central Standard Time. And I'm going to, and if you want to learn more about physics, you want to learn more about astrophysics and astronomy, please consider, if you're in that sort of stage in your life, coming here to the University of North Dakota.
Join us.
To do your studies. So there's a lot of wonderful things that we can definitely explore together. So I'm going to leave you with a quote, and that quote today is from René Descartes. And the quote is, "There is nothing so far removed from us as to be beyond our reach, or so hidden that we cannot discover it." Thanks for watching, and thanks for listening.
Thanks, folks. Y'all have a great day.